So then there are some other dirty things that I've done in the background that you can go home and try to figure out. Okay, because if I'm below the critical point, then this m squared is actually negative, right? But really, there's a lambda times 5 to the 4, so that it all works out. Okay, so just go to the new minimum and compute it around from there. Okay.
Means the follow-up condition for the 2-point Polish function you assumed like e to the power minus by chi square even below Tc. But
right.
That thing was derived at t greater than Tc, assuming that lambda to be sufficiently
correct. So the point is that if you take minus mod m squared 5 squared over 2 plus lambda by 4 5 to the 4th, you can actually convert this into plus m squared 5 minus average 5 squared over 2 plus lambda over 4 5 minus average 5 4. Okay, go home and do this little exercise. Okay, when m squared is less than 0, what happens is that what used to be like this becomes like this. Alright, and what I'm saying is that the curvature around here is what I'm now calling my m squared. And that is in fact nothing but the magnitude of t minus tc. Very simple calculation. You just go and do it and you will convince yourself that everything is okay. And as soon as I have an m squared here, I'll say I'll ignore the anharmonicity of the potential and just compute the correlation function. A simple minus. Okay? Good? Alright. Are we ready to go to RG? Or should we wait till tomorrow?
Sir, collision function.
Yeah.
Sir, critical exponent computed in that way would be same as like above TC. Like if I just expand around some minima and then.
Absolutely, it will be. It will be. Because again, the correlation function you're talking about below TC is a connected correlation function.
But like it misses actually around tunneling from one vacuum to another vacuum. That type of transitions are missing in this.
No. Why? Why is it missing?
If I just expand around a single minima and take
Oh,
a
but
particular.
remember, I'm doing Ginsburg-Landau theory. That's the whole assumption of Ginsburg-Landau theory.
Yeah, but
Is
then
that I'm
it
around
was
something.
non-perturbatively. Then I should have done it non-perturbatively. Like it's the perturbation theory.
I believe if you do it non-perturbatively, the action for that will be very, very large.
Very
Yeah, very large. It will be, it'll have something to do with lambda. It may come out with a 1 over lambda or something. Okay, and if lambda is small, you see that.
So that's not
Insanely, yeah. That's not really what's going on.
Okay. So this term will give me the right.
Well, depends on what you mean by right. Okay, this is actually not correct as we just showed, right? Unless d is bigger than 4,
Yes.
it is not correct.
No, I want to compute the correct exponent using there's this 5 for action. Suppose you have given me 5 for
Well,
this
but
action.
correct in what sense?
Like
The
so
correct exponents are really
my exponent is
the
given me from t above tc by assuming that my lambda is my m square is become positive.
no. What I'm saying is the following: that the mean field calculation, the Ginsburg-Landau calculation that we did, was based on some assumptions,
Yes.
right? The assumption was that you minimize the free energy and you look at small fluctuations around it.
Yeah.
The Ginsburg criterion is telling you that it is not correct if d is less than 4. Okay. Now the question arises: what to do next? Okay. So you're saying let's do the calculation exactly.
Yeah.
If you can do it, fantastic. Okay, but you can't do it. So that's why you need RG. Okay. All right.
Ginsburg criterion tells you that the mean field picture is not correct, right?
The Ginsburg-Landau picture is not correct.
Ginsburg-Landau picture.
The Ginsburg-Landau picture is not correct, very close to the critical point. Okay, it may give you a good description further away from the critical point, but at some point this criterion will fail. As you approach the critical point, it will fail at a certain distance in temperature from the critical point. At that point, you better stop using Ginsburg-Landau theory and do something more sophisticated. That's what it's saying.
But we have put the parameters from some like from mean field theory.
Right, so the mean field theory itself is telling you that it will fail. It's like a built-in feature. Right? It's telling you where it's valid and where it's not valid.
Yes, because we have done a Greenberg line on a mean field parameters. So is it
Yeah.
that we are, or have we done some feedback?
Greenberg lambda by itself
Is
is part of the mean field description.
part of mean field.
Right. If you go beyond Ginsburg Landau, then you have to do some arching.
Or
Okay? This is what Ginsburg Landau means. Okay?
So away from this critical point, it's well,
It's perfectly fine, yeah. It's perfectly fine, except that it won't give you the correct exponents, because the exponents really have to do with the behavior very, very close to the critical. Okay? Good. Look, when you have a theory, it's always very useful if the theory itself tells you that it's going to fail with some reason. Then you know that you can't use it there, right? Otherwise, you might just continue using it everywhere and get the wrong answer. Okay, so this is a very, very, very good feature of Ginsburg Landau theory. Okay, so now we need something more sophisticated.
I had a question.
Yeah.
That you started with the Ising model with just only the nearest neighbor interaction, and
Yeah.
for that you have gotten the critical exponent and you have written the Landau log x and all these things. But suppose you include the next to nearest neighbor interaction,
Right.
for that opens you will get the different critical exponent
No.
or the same.
It depends on whether the next nearest neighbor interaction is of the same sign as your nearest neighbor interaction. Supposing all the signs are ferromagnetic, then it actually doesn't matter. Unless you make the interaction very long in range, then it may have different critical exponents. But as long as it's some short range model, right, it will always have the same critical exponent.
And for different theories, like suppose critical Ising model or Potts model and all these kind of theories, is
Yeah.
there such kind of action exist? Means,
Yeah, there are different actions for, so what you really want to do is you want to identify the symmetries of the theory and the dimensionality of the theory. And that's supposed to be the only thing that matters for the critical exponents. And of course, the range of the interaction. So most of the stuff I'll be telling you, in fact all of it, is going to be for short range interactions. Long range is a very different story. Okay?
Even in like mean field study, we include the next nearest
Yeah.
neighbor interaction.
Yeah, you'll get the same mean field exponents. Because remember, every time you do the expansion, it's only the first power, the tangent hyperbolic. It'll be some more generalized analog of the tangent hyperbolic. But it'll again be some odd function. Right? Because the theory has a symmetry that you can have, if m is a solution, minus m must also be a solution. So when you say m is equal to something, that something had better be an odd function. Right? What are the properties of an odd function? It has to, basically usually starts with x and then it'll have an x cubed. So that is really all you care about, because the numbers in front of the x and the x cubed might be different for if you take different ranges of interaction, but the fact that there's an x and an x cubed will not change. Okay? Good?
One thing is that you are saying that we have to write the action on the symmetry and the dimension of the
Right.
So that is because this dimensionality can't come into it, because in this action language you can sum over all these stuff, and why is dimensionally important in
You can already see that if the dimension is bigger than 4,
yeah, for
it's very different than dimension less than 4. You can also see that the criterion itself is telling you that you will get bad faster and faster as you go to lower and lower dimension. Right? This criterion breaks down worse and worse if you go to lower dimension. Soon we will actually see more explicitly how dimension enters various things. Okay? Very soon. Maybe not so soon, because you guys are asking lots of questions, which is great. So maybe I'll only get to it tomorrow.
I am not
Yeah.
quite clear where in this picture this nature of interaction, whether it is short range of logarithmic coming.
Okay, so the short range interaction is really sitting here. Okay, this is where the short-range nature of the interaction is sitting in. Okay, so remember how I got this? I said this is really the same as S of R plus dI minus S of R squared, something like this, right? Okay, so that is like a nearest neighbor thing.
So this D is like coordination number.
No, it is much more important than coordination. Coordination number will tell you something about the coefficient in front of this. But whatever the coefficient is, I can always absorb it into a rescaling of phi. Okay, nothing else will change because this guy will still remain proportional to T minus Tc. It's not coordination number. Okay, so if I take a triangular lattice or a square lattice in 2 dimensions, they will have the same critical behavior. The critical temperatures will depend on the coordination, but not the exponents. Okay? It's much more, dimensionality is much more powerful than just coordination. Okay? All right? Okay. So let's do what is called Wilsonian RG. Okay, so this is the modern way of doing RG, and this was introduced by Wilson in the late 60s and the early 70s. So before that, there were some attempts at RG, but they were more for very specialized cases. There was an attempt in quantum field theory to do renormalization group, but the point of view there was very different. The point of view there was that when you do quantum field theory, you always encounter infinities. And their idea of RG was how can we cancel infinities? Okay, but that's not going to be our point of view at all. Our point of view is going to be how do we integrate out the high energy degrees of freedom and get an effective low energy theory and keep on doing it and get fixed points. That's going to be our point of view. Okay? Later on, once you understand this, you can then go back and apply it to quantum field theory as well. And it works there also. Okay? So, what is this approach? So the idea is the following. So normally, when you have a lattice, you have some idea of a Brillouin zone. Okay?